properties of matter that we're going to exploit in a lot of our experiments is color, because color is relatively easy for us to observe, and maybe more importantly, color is also fairly easy for us to measure and quantify. So what is color? What causes things to be colored? Well, here I've got a pretty simple example. This is just blue food coloring in water, nothing all that fancy, but why does this appear to be blue? Well, the color that we observe is a direct result of the way that light interacts with this sample. What do I mean by that? Well, let's take a little bit closer look at what this solution really looks like. So let's start with a test tube full of liquid. All right. Well, we said our sample was blue, so if this sample appears blue, that must mean it has some, blue particles in it. So let's give it some blue particles. There's our sample of blue liquid. So if we as observers look at this liquid, it appears blue to us. Well, why does it appear blue? Solutions have color because of the way they interact with light. Different particles will absorb or reflect light differently. So what if I take some orange light, here's my blue sample. What if I shine orange light on my blue sample? What's going to happen? In order for a particle to be able to absorb light, it kind of has to interact with that light. So let's extend a few of these rays of orange light. Well, that one looks like it made it right through the test tube. This one looks like it bounces off of that one a little bit and probably bounces off that one, probably gets completely absorbed between those two particles. This one looks like, well, it runs right into that. This one gets close to that, so maybe it's affected a little bit. This one, again, looks like it probably passes right through. So one of the ways we can quantify color is by looking at how much light we're shining on the sample and observing how much light is coming out of the sample. We can think of that two different ways. We can think of that either as a percent transmittance, or we can think of that as an absorbance. And for a number of reasons, chemists tend to think more in terms of absorbance, especially when we're thinking about light that's in the linear wavelengths of light. So how is the absorbance of a sample related to what's in that sample? Well, let's think about the factors that can affect the absorbance of light. First of all, what about these absorbing particles? If we have a particle that can interact with, in this case, orange light, well, then it might be able to absorb it. So that's really a fundamental property of these particles. So we have to think about particle type, because the particle has to be able to absorb the color of light that we're shining on the sample. What else? Well, why did this piece, or why did this ray of light pass through? Why did this photon make it through the sample, but this one didn't? Well, because this one ran into a particle, this one didn't. So what if we have more particles? Obviously, more particles are going to give more opportunity for the light to absorb. So concentration is also an important factor in the absorbance of a solution. And finally, this one is actually very closely related to concentration. What if I keep the same concentration but I make my test tube bigger? What if this photon of light just physically has to pass through more solution before it can escape out the other side? Well, probability says that then it will have more time, it'll be more likely to encounter a solute particle, an absorbing particle in the solution. So that is what we call path length. So the absorbance of a sample is determined by these three things: the type of solute particles we have, the type of absorbers that are in solution, the concentration of those absorbers in solution, more particles, more absorbance, and the path length of the solution, or the amount of solution that the light has to pass through before it escapes. These three factors are all related to the absorbance of a sample through a relationship called Beer's law. So Beer's law tells us that the absorbance of a particle, or the absorbance of a solution, is equal to epsilon LC, where epsilon is essentially a measure of the particle type. Epsilon tells us how absorptive each particle is. L is the path length, and C is the concentration. Now, what about that epsilon? It goes by a number of different names, so depending where you look it up, you'll see this referred to as molar absorptivity, you'll also see it listed as the term that I tend to use most often, extinction coefficient. And there are one or two other terms you might run across, but these are probably the most common ones that you're going to get. And again, by default, if I'm talking about it, I'll usually call that an extinction coefficient. So that's Beer's law. Let's take a look at an actual example of a colored solution and how Beer's law can affect what we're talking about when we look at that solution.